Alrighty, guys. Can you hear me? Yeah, that sounds good. Right. So let me start by asking if there are any questions from the last lecture that you guys might have. If that's not the case, then we're going to start. Today's lecture, right? So this session here is going to get recorded, and then after we're done, we'll post it on. I'll post it on YouTube, and that'll be a link on Canvas. Right. So what we're doing now is we're going to get started on the main text. So again, this is Abbott's, and we're going to start in the first chapter. Right, so we're going to start over here in the first chapter. My plan was to talk about a little bit about the first 4 sections today. So 1, 1, 2, 1, 3, and 1, 4. And then we'll talk about cardinality next Wednesday. So some of this, I'm guessing most of this you will have seen in 300. But yeah, there might be some redundancy in what you've seen before, but hopefully there'll also be some new things today. So let me try to get started, and when and if you have questions, by all means, just either write in the chat or ask questions, right? So we're starting out in so this, hopefully today we'll do sections 1.1 to 1.4, and we're going to start out with some sets that are all familiar to you guys, right? So when we write the natural numbers, right, so those are the numbers 1, 2, 3, 4, and so on, right? The set of natural numbers. that one we've seen, and then we'll have the integers. The integers will be the same. It'll be a bunch of numbers, -2, -1, 0, 1, 2, and so on. Right, so up here is 0 is typically not included. Typically not included. And then we'll have the so those are the integers, and then we'll have the rational ones. Those are the ones that have the form P over Q, where P is integer, right? So it's one of these numbers, and Q is something in the natural numbers. But these here are the rational numbers. And it is custom to very often choose the smallest representation here. So we often pick, so we will often pick P and Q with no common factors. Right. And it's just, what do I mean by that? Well, if we replace a P with 2P, and you replace Q with, say, 2Q, right, then I'll have P over Q. Well, this will obviously be the same thing as 2P divided by 2Q. So it's not like this representation here is unique, but if you delete these common factors, then we're good. So we'll often pick these with no common factor, Right, so we will say, we'll write a half, like 0.5. We'll write this as 1 over 2 and not 2 over 4. Right? We would prefer to write it in the first form. Of course, they're the same, we get it. But when we talk about representation of rational numbers with no common factors, what it just means is that we have factored out as much as you could. So 2 over 4, we can do better than that and write it as 1 over 2. Right, and then the real analysis, this is of course about the real numbers. So the real numbers, this is the interval from -infinity to infinity. And but what is that? So that's one issue that I want to talk about today. Like, so we're pretty comfortable with N, Z, and Q, and we've seen R a million times. How do we construct R from Q? How do I get from this setup here, which is given as these ratios, to getting R here? And right, so it's clear. So we want Q to be inside R, but it could be bigger. But R is going to be bigger. But R is going to be much bigger. And let me just look at a little example. The example is also in the book, and there's a similar example in the homework, and you've probably already seen this example. But nevertheless, let's just look at an example that illustrates that why is it that we just don't want to have Q? Why is it that we want to enlarge Q to something bigger? And so one example is to say that the square root of 2 is not in Q. So this is a quantity that we don't have in Q. So, and how would one go about proving it? So argue by contradiction. argue about contradiction and write and say that you would have it, then what would that mean? So that would mean that P over Q, if I squared it, I would get a 2. This here is my square root, right? I square it, and I'm gonna get a 2. So say this for what P is going to be our number in Z, and Q is going to be the number in the natural numbers. So we're going to argue about contradictions. If we're going to find a contradiction, let's try to find it. And again, these are going to have no common factors. No common factors. Well, we can factor out here. So we can write this here as P squared Q squared. This is equal to 2. This is going to be the same as saying that P squared Q squared times 2, right? So that means that P squared is even. Right, so this here is going to imply that P squared is even. But then we're also going to get that P is even. So if P is even, say P is equal to 2 times R. R is an integer. And then what? So if P is even, it's 2 times an integer. Then we go back and plug it in. We go back and plug it in here. So we'll get, so if I want to continue these implications, I will then get, I'll get from here, if I put in P, I'll get 2R squared is equal to 2Q squared. That's going to be the same as 4R squared is 2Q squared. And then I'll divide through. I get that 2R squared is equal to Q squared. So now we have exactly the same situation as what we had up here. That means that Q squared is even. That means that Q is even. This is going to imply that Q squared is even. Well, that's going to imply that Q is even. So now I have that both P and Q are even. So they have a common factor of 2. So both P and Q have a factor 2 in it. So P and Q have a common factor. Here will be 2, and this is a contradiction. I write contradiction like this. Because the starting point was that they didn't have any common factor. And now I went through it, and they had a common factor. So that's a contradiction. And that means that I've made an assumption that is not valid. So, and the assumption I made was that I could write, the assumption I made was that this was indeed in Q. So that leads to a contradiction. That means that it is not in Q. So this is one quantity which is of interest, and we don't have it in the rational numbers. So if I want to be able to take square roots, I apparently need to move beyond Q. Does that make sense to you guys? So if you want to take square roots, and we do, we we are no longer in Q. So we don't have, so even if I take a number, say Q and Z, we don't have that the square root of Q belongs to the rationals. So we need to add, so enlarge Q, enlarge Q to get this property. I mean, sometimes, and this is, maybe we'll talk about that at some point, like in complex analysis, we go one step further. It's always the square root that is the troublemaker. We go one step further and consider like the square root of -1. This here is also not going to be a real number, right? So this is not going to be a real number, right? So here we need to enlarge even R to deal with square roots of negative numbers. So this is in complex analysis. So here we're just doing, I don't think we're going to do any complex analysis in this course, but there is a need to go beyond the real numbers as well, but we won't go into that here. All this example here illustrates is that there is a need, if you want to do square roots in general, to move beyond the rational numbers. So how does one get, how do you create these rational numbers? So how to create R from Q? There are two standard ways of doing this. The first way is using something called Cauchy sequences. This is coming on page 66. And the other way of doing it is these cuts, Dedekind cuts. This is coming on page 298. And it's a little bit ironic that we're doing real analysis, and the existence of these real numbers in our textbook, book, it's on page 298. And there are 8 chapters in the textbook. Right, so you go all the way down to the very, very last section. And this is when you'll finally create R from Q. And he writes about it. If you flip, get your hands on the book and flip to the back. He writes about it. He says that there's something ironic about having the final section be about constructing this number system that has been used throughout the entire book. And that's how he presented. I mentioned some of the other books that we could have used, and so here is the Baby Rudin book that I mentioned in class. And if you do the Baby Rudin book, you can see this is the one that I have. This is dating back to the mid-50s, the 60s, and the 70s. So this is an old book, and it takes you through many of the same topics. And you'll see here that he gets to it on page 17. And if you flip over here to his page 17, what he's doing here is that we will construct R from Q in this appendix. And again, he's using these cuts, these Dedekind cuts. There's a discussion over here in the end about how could one also try to create these real numbers, and he's mentioning what I'm mentioning in here. He could go in and use these Cauchy sequences, and this was originally done by Cantor that we talked about last time. Okay, so we're not following Rudin. I'm just mentioning to you in case you will be curious about where you can find such a construction before you get to the very end of the course. And so we're going to be following Abbott, and the way that Abbott he gets around this. Right, so we follow Abbott. So we will follow Abbott, and the way that Abbott he gets around it is he places this is Abbott. And Abbott he places an axiom that R must have, and this axiom he refers to as the completeness axiom. Other textbooks will call it the supremum property. The completeness axiom was a supremum property, and some of you, I'm guessing most of you, will have seen the supremum before, but let me just recall it. The supremum property is that you pick a set, any set inside R, which is upper bounded, for any subset of R that is upper bounded. So let's just recall what it means to be upper bounded. So what does it mean for a set to be upper bounded? Well, it just means that there is a B in R, such that when I take anything inside the set, I'm less than that number. So there exists a B such that for any A inside the set, I will have that A is less than B. Right, so we take a set that is upper bounded. For any such set, there exists a quantity which is denoted by sup of A, and this is an element inside R with two properties. So this sup of A has two properties. So first of all, it's a big number. Sup of A is a big number. So for any A in A, we'll have that A is less. Maybe I should write it in the other direction. This is the more common way of writing it. Let me write it the other direction. So A is less than sup over A for any A in capital A. So sup A is a big number, and it's a small big number, right? So here we're saying that sup A is big. Sup A is a big number, and this one here is going to say it's the smallest biggest number. Sup A is the smallest big number. Right, so what does that mean? Well, if A is less than A prime for any A in A, so if there exists an A prime in R such that this is true, well, then A prime is going to be big. So we'll have that the sup A is going to be less than A prime. If there is such a number, which is also a big number, so it's going to satisfy the same inequality as sup does, the first one here, well, then sup is going to be smaller than So sub A is a big number, but it's the smallest big number. So this is what Abbott, he says the numbers that we're working with, these R's, is going to have this property. And so this is what he calls the completeness axiom. So when you're talking about how to create R from Q in terms of these sequences here, well, you better make sure that whatever you're doing satisfies then ultimately this this axiom here. So when you go to page 298, all the way to the end of the textbook, whatever construction they have there with these cuts that you're talking about, it should be a consequence of that you have this axiom. So what I had in mind for today was that we're going to be looking at some examples. I know I asked TA to talk a bit about sup and also infimum. So here I just wrote it down for the supremum, but maybe we could look at a couple of examples and then see how to compute the suprema. Maybe also look at an example that will show that this completeness axiom, it does not hold for Q. You really need more numbers than just the rational ones. Let me define infimum first. There's also there's a variation of this completeness axiom which is completely equivalent, but this one is the infimum. So the infimum. So again, you take a set A in R. Now it's not going to be upper bounded, it's going to be lower bounded. So let's just recall what it means to be lower bounded. It means that there exists a number which is small, so say a minus a b in the natural numbers, such that for any a in the set, a is going to be bigger than b. So it's bounded from below. Then there exists the infimum. This is denoted by inf of a. So you take this set, then inf of a satisfies the two properties up here. Just adjust a little bit. So the first one is that inf is small. Inf is a small number. Okay, so that's the first property. Inf is a small number, that means that the infimum over the capital set A is less than A for any A. But not only is it a small number, it's the biggest small number. Inf over A is the biggest small number. So that's the second property. That if you can find another one, so say that if A prime is another number that satisfies this property. So if this guy satisfies that A prime is less than A for any A in A, then A prime is going to be bigger then A prime is going to be smaller than the infimum over A. So it's the biggest small number. And we should say in all of this, we require that the supremum of A, so A upper bounded, and the infimum over A, so this is for A lower bounded, we require that these quantities, belong to R, but not A. So super and inf, the real numbers, do not require to belong to the set A itself. And this can be a bit confusing. And this here has to do with, so this is the difference. there's a difference to max and min. We're not using the words max and min on these previous slides. And let me try to look at some examples here. Maybe we can make more sense out of these notions. So I have 5 examples prepared, so let's try to walk you through some of them. So if I will take a set, this is 1 over n. N is an n. So what do we have inside here? Well, this here is going to be equal to, it'll be equal to 1, a half, a third, a fourth, a fifth, and so on. So this set here, it is, what is it? It is bounded. It's this set here is something that sits inside the interval, say 0 to 1. Right, so this is a bounded interval. This is both upper and lower bounded. Right, so we have inf and sup. Okay, so let's try to work out what they are. So what is the infimum? Well, the infimum is going to be a small number, and it's going to be the biggest small number. Right, so we could say, we could start out, what could we take? So we could start out with, say, minus 10. Would that be a good infimum? Well, is it a small number? To be a small number, it means that it has to be less than or equal to everything that we have in here. So that's great. Is it the biggest small number? Well, could we come up with another number that would be bigger than this one? That would still be. Brian is saying no way. And Brian, can you give me a number, such a number? Which one would you take? Instead of minus 10, you would put, what about minus 8? With that one, that is definitely bigger, and it will still be less than all of these. Can we do 0? So 0 is good. This is good. 0 is less than all of these. 0 is less than all of these. So this one here I like. Could we make a little bit bigger? What about 0.1? Would that work? Well, not quite, right? Because how small do these numbers get over here? Well, at some point I'm going to get past 1 over 1,000. I'm going to get past over 1 of a million, and it keeps going. Right, so at some point this number over here is going to be very, very small, and this one here would not be a lower bound. So this one here doesn't work. This is our winner. And we should just note that 0 here does not belong to A. And that means that 0 is not a min. 0 is not a min. And indeed here, if I look at the min over A, it does not exist. There is no minimal number inside the set A. But there is, of course, an infimum, because this is a defining property of the real numbers. And so that's good. What about the supremum? If I take sup of A. So now I'm looking for a big number. I'm looking for a big number, and I'm looking for the smallest, biggest number. Shin is saying 1. I like it. That is good. And Shin, is this here also, is it the same story as the min, or is this a max? this is also a max. And that's because we can find an n in here such that we get exactly 1. Indeed, you just choose n to be equal to 1. Okay, very good. So let's move on to another example. If I would take a to be, say, the open interval from 0 to 1, this is definitely something inside R, and it's again bounded. Bounded from below and bounded from above. In this case, I will take the infimum, I'll take the supremum. Any guesses on what they are? Any guesses on what the inf and the sup are? I'm looking at numbers between 0 and 1, this open interval. What will be the smallest, what will be the biggest small number, and what will be the smallest big number? Inf should be 0. That's right. This is not, is it a max or is it not a max? The other one should be 1. This is not a min. And this is not a max. Very good. It's time to make it a bit more complicated. Let me find the next one. So let me try to look at this square root problem that we had before. Let me look at the set A to be, it's those rational numbers, and so those rational numbers such that R squared is less than 2. And so if I look at this set here, maybe I'll try to make a picture. So if I'm just pretending that I have R down here, if I'm pretending I have R down here, I'll have the square function. So it'll be, if I look at something like this, this here is my, so let me call this for x. Right, this here is my x squared. And so I'm interested in the threshold 2. So let me put in a 2 here. This here is 2. So what are the x's that I'm looking for? I'm looking for those numbers such that the square is less than 2. Okay, so I'll go down here. So I'll go down here. This will be minus root 2. And this will be root 2. If I take the sup over A and the inf over A, what would I get here? Right. Again, this is bounded. This is bounded, right? This is going to be at least going to be a subset of what, minus 10 to 10. Right, so it's a bounded set, so there will be an inf and a sup when I'm looking at it inside R. So what are these two guys here going to be? Well, how close can I get to the square root of 2 when I'm moving around in the rational numbers? Can I get arbitrarily close to this one here? Can I get arbitrarily close to this one here? What do we think the sup and the inf are? sup is square root of 2, and the inf and these things here, they're not in Q. That was the first thing that we did. They're not in Q. But they are, they're going to be by this axiom that Abbott wants us to use. These quantities, they are going to be in R. Because they are supremum and the infimum. But they are, the supremum is indeed an R, and the infimum is also an R. I had a few more examples in mind. I wanted to show you just a bit about how one could try to go about maybe studying these things here for if I would look at something like I would take an example like what would I get if I would take an example like 3n minus 2 divided by 2n, and then I would have n be a natural number. So I could factor out here. This would be 3 divided by 2 minus 2 divided by 2n, right? So that's minus 1 over n. So what would we get here? We would have the infimum. I want to make this thing small. How small can I make it? That was similar to one we had before. If I want to make it small, I want to subtract away as much as possible here. So should I make n this? And then I want to make n to be as small as possible. So that'll be a 1. So this would be 3 over 2 minus 1. So this would be something like a half. Right, so it's very similar to before. This is going to be my min because n equal to 1 works. And if I take the supremum, over A, then I don't want to subtract anything. So I want to pass n off to infinity. I want to pass n off to infinity. I'll get 3 over 2 divided by, and then minus 1 over something that's humongous. So this is going to be small. This is going to be 3 over 2. And here there's no max. Okay, so this was very similar to what we had before. But it does show you something about this 3 over 2. I can move this set 3 over 2 somehow outside. It is irrelevant for taking the supremum. And all you need to focus on is where you have this parameter n that is moving around. So by the same token, let's try to look at something like, set. So here I have t plus 1, and then I'll divide by t minus 2. And now I'll take t in the interval 2 to infinity. Something like this. And now it gets much more tricky. How would one go about doing that? It's always advisable when you get into a situation like this one, where you have an interval and you have this function, you want to study what happens to the function, this ratio, when t is equal to 2 and when t is equal to infinity. Okay, so the way that I would do something along these lines is, and that's what I want to, so there are some benefits to Zoom teaching, and let me show you one of the benefits to Zoom teaching. So I'll go in here and I will share my Mathematica screen. Can you guys see Mathematica? That's the green box that's flickering. So the function that I'm interested in is f of t which is equal to t plus 1 divided by t minus 2. That's my function. And I'm curious to see what happens when t moves between between 2 and infinity. Okay, so the way that I can study that is by plotting it. It's always a good idea. So plot f of t, and then I'm plotting it between t and say 10. And you can see how it looks like. It sure looks like this function here blows up when you get closer to 2, and then it decays. And it looks like, where does it go? Where does it go when you get up to be big? Well, maybe you can plot it out to 1,000. It sure looks like it's going to converge to 1. It sure looks like it's going to converge to 1 as t goes off to infinity. All right, so by plotting this function, we have a pretty good idea about what to look for. One thing we'll be looking for is that around 2, the thing blows up, and around infinity, the function goes to 1. Okay, was there a question in chat? Yeah. So we have an idea about what to do now, and now we can go back to our piece of paper and see if we can get this thing proven. So how do I get it to work? How do I get it to work for t equal to 2? Well, for t equal to 2, if I look at the limit as t goes down to 2, then I'll have t plus 1 divided by t minus 2. But the top part here converges to 3, and the bottom part converges to 0. This thing here is indeed equal to plus infinity. So this means that the set A here is huge. This is not bounded from above. So A is not bounded from above. If you want, you can then say that the sum of A is equal to plus infinity. Lots of people do that. It is not bounded from above. What about the other way? So we're also interested, this is what happens when you go to 0. No, when t goes down to 2, and now we also want to send t off to infinity. And how do we do that one? Well, then we want to take lim of t up to plus infinity of t plus 1 divided by t minus 2. And how would we do that one? Well, most students are going to say something like, let's apply L'Hopital. So we can do that. And then you get 1 over 1, this will be a 1. There is a better way. This one here is this is not always a good, I mean, L'Hopital's rule of course works, but very often it is much faster to use Taylor. I'm going to put a problem on the homework at some point where you can try to do something like this using L'Hopital, and I think you have to compute 100 derivatives to get this thing to work. And if you use Taylor, it is much faster. But for this particular problem here, it doesn't really matter. Right, so it converges to 1. And what was the other thing that we wanted to see? We wanted to see that if is decreasing. Right, so the picture we had was that it goes down like this, and now we know that it converges out here to 1. Right, so what would we guess? In between, we need to check that f of t is decreasing. How would we check that? Well, it's a smooth function, so we need to show that f prime of t is negative. And if you're not used to using Mathematica, so you can either do this by hand or you can use a Mathematica. And let me just show you, if you wanted to see how it goes in Mathematica, how So you have your function, right? So my f of t is this guy. And if I want to compute f prime, Mathematica can simplify it, and you get something like that. And you can see the coefficient is negative, so it's a decreasing function. You can also compute this derivative by hand, plug it in, and of course you'll get exactly the same expression, and it's negative. Using Mathematica like this, I personally like it because it's quick and easy. This is negative, so we have a decreasing function. So if I am to look for where the min is going to be, that means that the min is going to be out here in infinity. So if I look at the infimum over A, what is it going to be? It's going to be that 1. And so this is absolutely right, Chenya. And can you also tell me if this is a min? Is this a min?
No, it's not.
Not a min. Ready. If you're getting a hang of infant soup here, maybe we can do one more. Do one more example. Let's do one more example. Page 7, page 8. One last example. Let's do A to B. The last one I have is n squared divided by n plus 3. How would I start with something like this? Well, the way that I would do it is exactly the same as what we did before. Forget about the n, write a function, g of t. G of t should then be t squared divided by t plus 3. I'll just take t here, the smallest number, this is 1, so I'll take t bigger than 1. Okay, I'll go back to Mathematica. I have my g of t. It's going to be t squared divided by t plus 3. And then I want to plot. I want to see how the thing looks like. And t was going from 1 to say 10. And that's my line. Okay, so it sure seems like this is an increasing function. It is an increasing function. It's finite at 0. Before we had explosion at 0, and then it increases. Okay, so let's see how maybe we can compute the derivative just to make sure that it really is increasing. So we'll take g prime of t. And this looks good, right? This is positive. T is a number that's bigger than or equal to 1. This is a positive number. This is an increasing function. So I'm looking at this, I'll get the min, the inf is going to be attained over here, close to 1, and then the max, this is going to be out at plus infinity. So let's try to make that a little bit more precise. So this is an increasing function. Okay, so if it's an increasing function, I just want to have t equal to 1. So the infimum of A, this is going to be exactly where I put n equal to 1. So it's going to be 1 divided by 4. And this is also a min. Now, it's an increasing function. Okay, so let's try to figure out what happens here. I have t squared over t plus 3. So how is the behavior? When you look at the highest powers, this g of t, when I take the limit as t goes to infinity, I can use L'Hopital again, or I can just look at the powers. This here is going to be the same thing as the limit as t goes to infinity of t squared divided by t. This is t, this is equal to plus infinity. So this is my supremum. This is unbounded. So the set A is not bounded from above. right? So if you want, you will set the supremum to be plus infinity, right? And it's not going to be a max. Okay, so we've done a bunch of examples. Are there any questions about some of these examples? Brian is asking if we can go over the soup. Yeah, so this is just the way that the textbook says it. The way that the textbook says it is so this is Abbott. Abbott, he says soup is only defined for soup A is only defined for A inside R bounded from above. And then in which case, in that case, soup over A is going to be a real number. Right? So me and most mathematicians and most math folks, they allow for A arbitrary. They allow for A arbitrary, and they allow for the soup of this set here to take values in the interval up to and including infinity, right? But of course, plus infinity, this is not a real number. So when A is not bounded from above, we set the soup of A to be plus infinity. And in the example we have here, this set here is bounded from below, but it is not bounded from above. And the reason it's not bounded from above, this is what we get out, for example, by looking at the picture. Let me just bring it up again. Like the set A that we're looking at is what's up on the y-axis. It's what goes from here and then upwards. And this straight line here is going to continue going. So there's no upper boundedness in the set. And the same thing is true for the previous one. Here, the sort of points that you can reach, but this thing here blows up to plus infinity. So the soup in both these cases will be plus infinity. It's just Abbott, he always insists on having a bounded set, and then he will say that the supremum is a real number. When you have a bounded from above set, then the supremum is given to be a real number. And what I'm saying is that we can actually talk about suprema for general sets. It doesn't have to be upper bounded. It's just for those sets that are not upper bounded, you'll always end up with a supremum that's equal to plus infinity. And the same thing, similar. If A is not bounded from below, we set this infimum to be minus infinity. Okay. Any other questions? So we did a bunch of examples. We're doing these examples because I know it's in the homework, and I know this upcoming quiz here is also going to have a stack of these examples. But I also want to prove some theorems. This is a math class where we want to do theorems. So let me do some of the results that's in Abbott's first sections. So let's do some theorems. The first one, Abbott calls it a lemma. He says take a number. He calls it S. So take a number. Let this thing be an upper bound, not necessarily smallest. Let this be an upper bound for A. And A is a set. So remember, an upper bound just says that you take anything in the set, A is going to be less than the upper bound S, no matter what point you pick. So then the lemma says, the lemma in Abbott that I want to prove, it says that this number here, this upper bound, also has a smallness property. So S is equal to the supremum over A. And this happens exactly if and only if. And here comes the statement. It says for any epsilon, so for any epsilon, you can find an A such that if I just subtract a little bit from this upper bound, I'm going to be strictly less than A. Right, so for any epsilon, you can find an A, right? So this statement here, it means that this A here you can find, this A can depend upon epsilon. So when you read the quantifiers, you read the way that you read quantifiers is you start out here on the left and you read in this direction. So it says, you give me this for any epsilon arbitrary, you can find an A such that this statement holds. This is the same thing as saying that S is, so it's not just an upper bound, it's the smallest upper bound. Okay, so, and it's an if and only if. Right, this one here is, people either write it as if with two F's. You can also write it as if and only if, or you can write it as equivalent. Some people also use the word double implication or by implication. I'll be using the words if and only if. So you give a proof. And if there is an if and only if thing to be proven, there are two things you have to prove. You have to prove a down direction and an up direction, right? So let's start out with the down direction. So say that S is not just an upper bound, it is indeed the smallest upper bound there is. Then what we have to do is we have to prove the statement. Right, so let epsilon be arbitrary. Then it holds that if I take S minus epsilon, this is less than S. Right, so S minus epsilon is less than S, and this is because epsilon is positive. Right, so therefore, S minus epsilon, this is strictly less than S. So there's no way that S minus epsilon, this is not an upper bound. Because otherwise, you would have a conflict with S being the upper bound. So if this is not an upper bound for A, well, if it's not an upper bound, that means that there is some A that is bigger. And that was the conclusion of the first part. Right, if it's not an upper bound, you can find something that is bigger inside A. So this one here was typically with these double implications, there's an easy way and a hard way. And the hard way here is the up direction. And very often the hard way is the usual, this is the useful way. There's this property here that will characterize the smallness property. So what we want to do is we have given that S is an upper bound, and we want to prove that this property here encodes the smallness property. And we want to show, we want to see that S is the smallest upper bound. It's the smallest upper bound. Okay, so to do that, you're going to take another upper bound. So let B be another. Let B be another upper bound. And then show, right, so let B be another bound. What does it mean? It just means that A is less than B for any A in A. And what we want to show is, we want to show the smallness property. So we want to show, that S is less than B. And the way we want to go about things is argue by contradiction as before. So let us argue by contradiction and assume, let's assume the opposite of what it is, the negation of what it is we're trying to prove. So let's assume that S is big. And now I have to create a contradiction. And the way I'm going to do it is I'm going to set my epsilon to be this difference, S minus B, which is positive. Then I go up, I'm proving the up direction here. So for any epsilon, I have one now, I can find an A such that this is true. Then there exists an A such that S minus epsilon is less than A. But I know what the left-hand side is because I have a definition of epsilon. This is equal to S minus, and then parentheses, epsilon is S minus B. And the S's cancel out, and I'm equal to B here. So now I'm getting here that B is less than A, but that is impossible because B was given to be an upper bound. So this here is a contradiction. So this is a contradiction. So we have this, we have an equivalent characterization of this smallness property that the soup has. So soup, again, this is a big number, but it is the smallest big number. And this property here, this is what encodes this smallness property that the supremum has. I should also say that we're going to see variations of so later we will see, we shall see, I should say more specifically, we will work with quantities that are called lim sup. So you see the supremum is here again. This is also sometimes denoted by lim, and then there's a line on top of it. And we also work with lim inf. This is also very much denoted by that guy. We'll work with these things here instead of lim. So they're going to be a lot more common with the supremum and infimum, we'll even combine them into lim sup and lim inf. And this is going to come later. And these are going to be characterized again about these. It's going to be something that is big, but it's going to be the smallest such big thing. Are there any questions? We have a little bit of time left, and I know what's going to come in your first quiz. So let me just, I wanted to say a little bit about that. I saw your first quiz last week, and this here is in section 1.4. This is related to your quiz number 1, and it has to do with a theorem that's in there. This is this nested interval property. And what you do is you take a bunch of intervals that are nested, very much like the ones that we had for the Cantor set. So the decrease, exactly like the ones we had in the Cantor set the other day. So the decrease. And then the theorem, what it says is that the intersection, when I intersect all the way out to infinity of these sets, I'm not going to get the empty set. This is the nested interval property. I take these closed intervals. So this here is for closed intervals. If I take a nested sequence of closed intervals, I do not get an empty set in the end. And this is very similar to how we created the Cantor set. It was not just intervals. We had each interval consisted of a number of smaller intervals, but we had exactly this property that when we did the intersection, we will get the Cantor set. And the thing I want to say here is that this doesn't work in general. This doesn't work in general, and it's highly related to this sup and inf that we've been talking about. So let me just maybe give a couple of examples here. So the first example that one could do, and this is where it doesn't work. So here's an example for where this stuff doesn't work. So if you take the intervals to be like 0 to 1 over n, I'm going to keep them open now. And then I'll let this be inside, say 0 to 1 over n plus 1. And it keeps going. N is a natural number. So here, this is like 0 to 1, contains 0 to a half, contains 0 to a third, contains, and so on. It doesn't work in general because in this case, we will have that the intersection of these intervals, this is empty because again, if we indeed would have an x inside that intersection, we take an x inside this intersection, so we're again going to argue by contradiction. If I have a guy in there, I have a point in there. If I am in the intersection, I need to be everywhere. Right, so if I have such an x, well, then I would have to have x in everything. Right, I belong to the intersection if I am in every single set. So x has to be in this thing for any n. But then in particular, I have to have x is positive and it is less than 1 over n. And that doesn't work because if I take the limit, into infinity, but if I take the limit here, so I have that x is less than or equal to, So remember, when you take a limit, you need to put an equality sign here. You cannot keep the strict inequality of 1 over n, and this is 0, right? So I'm getting here that x is strictly positive and it's bounded by 0 from above. This is not possible. This is a contradiction. So that doesn't work. This nested property up here, it works for closed intervals. It doesn't work for these open intervals. But so if you want to have an example for where it does work, we could change the example from before. And instead of having it open, I could put it closed. And so if instead we will look at the interval from 0 to 1 over n, but now closed, this would have this nesting property. Right, and in this case, what would the intersection be? What would the intersection be? The intersection would be exactly 0. Very good. Very good. I think this is what I had in mind for today. I have a few more things prepared, but I think this is 14 pages of notes. I think this is plenty. Are there any questions before we disconnect?
For the homeworks,
Yeah.
for the first homework, can we state what the answers are the way that we did in the lecture today? Or do you want us to prove why those answers are correct?
It's always a tricky thing. So let me just pull up the homework and maybe we can talk about it. How many details should you include? I mean, in general, when I get a question of this sort, so your point is spot on. How many details should you provide? So if you can write down the correct answer, and you can feel like this makes sense to me, I would be happy. My concern there is that there will be some students you can just make a guess, right? And then what? If you guess the right thing, but you don't really know how to argue that this is the right thing, then it's a problem. So there's a difference between being able to write the correct answer and then actually knowing why it's true and just being able to write it. And this is a lot more up to you. Do you feel comfortable about the reasoning behind writing this right answer? If you feel comfortable about it, write a few lines about it. In general, my handing in homework, and the same thing is true with the exams, this is not going to be like each question. It should take no more than a few lines to answer. This is not like half a page or a page that you need to provide of documentation for each question. This is not the case. If you're doing that, this is not what I had in mind, but a few lines for each answer. So the difference between just guessing and then like for multiple choice, this is in these quizzes, you will have a number of multiple choice possibilities, and then you don't want to be guessing because there might be negative weight on them. I forget how he has set it up, but in the past, when I've done multiple choice, there'll be a negative weight assigned to it. And then this is a bad idea. So here, this is about practicing. Like, can we figure out what this union, we already did that intersection there, right? You already know what problem 1.2 is. And I'll be happy if you could write something like, well, 0 is in all of these half open intervals on the right. So therefore 0 must also be in the intersection. But there's going to be nothing else. Because if there was anything else, then it would have to be in all of them, and 1 over n goes to 0, so that won't work.
That's perfect. Thank you.
I mean, I can show you what I have written, right? And mine are probably very, very simple. Like this is that was what I had in mind. So, yeah. Yeah, don't write these long, elaborate answers. This is never what I'm looking for.
Thank you.
Yeah. Are there other questions? There was one in the chat. How can we prepare for the quiz? So again, the quiz this year is going to be about that nested property. And so what the quiz does is that it will state the theorem, and then there'll be a number of multiple choice questions following it. So, and there'll be a lot about this superinf. This is going to be essential in there. So you try to prepare, read the textbook, and see if you can follow some of these calculations that we've done here in class. Again, as I said in class last time, I will. My hope is that these homeworks and also the quizzes, this is supposed to be a way for you guys to get some feedback. Did you comprehend these concepts that we have talked about? It is not about getting 100%, getting 98% correct. This is what the in-class tests are about. So these homeworks, this is more about like, did you understand what inf and sup were in this particular case? If you understood that, then this is fine. But if you didn't, if there was a problem with it, then this is feedback, and we should try to get this, whatever issue that is, we should try to get this fixed and then move on from there. Right. So if you're thinking about grades, the letter grades you're going to get at the end of the course, then you should not be thinking about them in context with quizzes and homeworks. You should think about those as those simply as a way for you to get some feedback on how it's going. Is it open note? The way that it is set up, the quiz that I have seen, everything you need is explained. It's a long file, so there'll be the theorem, there'll be a proof of a theorem, there'll be definitions of all the relevant quantities that are in there. So I don't think you need an open note because it's already provided in the document. I also don't know nowadays how one can did this idea that I'm not a big fan of putting such restrictions in there. This is I don't see how this can work very well with this remote teaching. So again, these quizzes, this is supposed to, when you take the quiz, this is kind of like, we would like to see where the students are with this material and if they can do it. And in particular, if there are some students that are struggling with it, you'll get feedback there and then come to office hours and come after class and ask some questions about it. And then we'll try to help you master this material. So we will have a much easier time moving on to the next topic. Are there any other questions? If not, let's call it a day, and then I hope everybody's going to have a good weekend, and I will see you on campus on Wednesday. Unless it's Wednesday one of these. No, I forget. Yeah, we'll see. I need to check to see if Wednesday is one of these days that have been moved around. It always happens around here. So anyway, I wish you a good weekend.